Imagine a breach spreading like a fluid through a rigid grid, moving far faster than any human can comprehend. In 2025, Anthropic reported an espionage campaign where a single AI coding agent independently orchestrated a multi-stage cyber attack. That autonomous system performed up to 90% of the campaign's labor. It mapped networks and harvested credentials at machine speed, requiring almost zero human intervention. These AI models have collapsed the traditional economics of cybercrime. Advanced, persistent attacks that used to require teams of experts are now extremely cheap, heavily automated, and relentlessly fast. If your defense relies on guessing an attacker's intent or trying to predict what an AI is thinking, you will lose the race against machine speed. This diagram traces the flow from intent to infrastructure impact. Notice the gap between AI reasoning and final damage. If an authorized AI agent gets compromised, its trusted identity becomes a liability. Defense has to sit lower, supervising the actual infrastructure action layer. Real damage requires a sequence of enabling conditions. To steal a file or encrypt a server, an attacker needs a continuous physical pathway connecting user identities, software tools, network routes, and specific data permissions. To stop an autonomous attack, defenders must pivot. We have to stop analyzing the psychology of the prompt and start mapping the physical roads the attacker intends to use. We do this by controlling the AI's infrastructure reach. We track precisely which assets a system can physically touch at any given millisecond. This live mapping is called a typed temporal hypergraph. It is a continuous, breathing map of every user, server, application, and database spread across the enterprise, updating as connections form and break. This chart breaks down the 6 stages of an agentic attack chain. From reconnaissance to exfiltration, every move leaves a structural fingerprint. To counter this, the Predictive Tensor Control Plane monitors these fingerprints, where every stage presents an opportunity for an infrastructure response. PTCP doesn't waste time reading the model's text or analyzing the source code of its payload. It strictly monitors network geometry to predict when a dangerous pathway is about to open. By doing so, it translates the abstract threat of an artificial intelligence into a visible, physical geography of connections that defenders can actively manage. Imagine a live attack. The system detects an anomalous bridge forming on the graph as an external tool strikes toward an internal key management system. The defense responds with topological caging, calculating the minimum cut set to sever the attacker from their target. Enforcement happens instantly. PTCP revokes an access token or isolates a compute workload, closing the path before they cross. By surgically caging the threat, the attack is physically stranded. We neutralize the compromised AI without having to shut down the entire corporate network. This brings us to the ultimate goal, a topological defeat. Notice the red X's cutting off sensitive nodes on the right. The attacker might still exist inside the environment, but because their specific pathway is gone, they are rendered physically harmless. The surrounding mission-critical systems stay completely online. Meanwhile, human operators retain total control, visibility, and forensic evidence through a strict governance layer. As artificial intelligence scales in speed and complexity, the most urgent question for defenders is no longer what an AI might think, it is what that AI can physically reach. By treating cybersecurity as a geographic problem, we can strand malicious operations before they cause harm, ensuring that the sheer speed of autonomy is finally checked by the strict limits of topology.